Jerome. And hi, everyone. Good afternoon and good evening for all the participants. Welcome to the third session of the online course of the Understanding the Challenges of Exposure Variability in the Workplace. This is the third session, which is the final session. I believe we are all very excited, especially in this session. We will have several exercises, using the Expostats. So without further ado, I would like to invite Professor Jerome to start his presentation. The screen is yours, Prof.
Thank you very much. Hello, everybody. Welcome for this last part of this small course. I will share my screen. Right. So today, part 5 and 6 of the course. So I will take some time to introduce Expostats and the other tools that we created at University of Montreal to help people apply the concepts that I described yesterday and Monday. And then we'll see with the remaining time, we'll do some exercises together using Expostats. So if you go to our website, this is the main page that you can see. Depending on your settings, you might arrive on the French or English version of the website, and you can use the flag that you see on the top right to select the language you prefer. I would advise doing that rather than having the translating facility of your browser translate into your language, because this auto translation function, it messes with the functioning of the tools themselves. So it's more prudent to select English, for example, here using the flag and use the tools in English, rather than select the French version and then have it translated automatically by your browser. So you can navigate our tools from that website. Some history about Expostats. So put the tool online in 2015, and as you can see, it was fairly amateurish. It was only in French, and I had written all the website myself using this used computer at the back of my office. And then in 2018, we published with a team of collaborators a publication in the Annals of Work, Exposure and Health, describing the science underneath our tools. And it was the occasion of redesigning the website and the apps themselves, and that's when we created what you see today. And in 2022, the American Industrial Hygiene Association recognized the usefulness of our tools, and we are now listed in the resource page from the AIHA, where they make a list of the risk assessment tools that can help practitioners to make risk decisions. So the approximately, it's not always easy to monitor, but the servers that we put the tools on, they are used approximately 500 hours every month by people all over the world. We also have a discussion forum. I think there's approximately 100 people or so registered, and there's not a new post every day, but you can see some of the titles of the topics that have been the last topics that have been posted on this forum. So one was a question about quantile plots, some question about sensor data. A month ago or so, we published a case study of silica in the construction industry. There was an hygienist asking me some data interpretation questions, and he kindly accepted to transform his question into a case study about what you should and what you shouldn't do with Expostats. So you see there are various topics that you can post your questions or comments or discussion topics on. So I encourage you to profit from that if you would like to participate, or if you have questions or comments about our tools. So the way the calculations work on our tools, so we have mainly three Bayesian analysis tools that you can access either from the web directly, as we will do today, or there's an offline version which you can download and install on your computer. But in essence, so the three tools are, one is the one that we are going to use today, because I think it's the one that would be most useful for day-to-day risk assessment, let's say. And it's the tool that allows you to make a risk assessment for a similar exposure group. And I would say it's like the main competition for traditional tools such as IHStat, that you may be aware of. The tool 2 is, if you remember yesterday, I mentioned the British-Dutch guideline that had the very specific step about verifying whether individual workers in your group might be overexposed, despite the group would be fine. So tool 2 is allows you to apply this guideline, and is actually a Bayesian ANOVA model, and so you can evaluate with tool 2 within and between worker variability. And finally, tool 3 is a reformatic of the first tool, but basically what it allows you to do is, let's say you have an Excel file where you put your measured concentrations, and then on a second column you indicated some other information such as the group of worker or the type of shift, whether it was night shift or day shift, or I don't know, the season of sampling. So any categorical information, and tool 3 is gonna allow you to make a comparative analysis between these groups. So it's not a specific Bayesian model, it's just the model in tool 1, but applied to, at the same time, to different categories of variables. So for example, also if you want to do a before-after comparison, before intervention, after intervention, you can use this tool to make the comparison and make the demonstration, for example, that you actually manage to lower exposure levels. So what happens is that you, from the website, you input your measurement data, and the data is treated on our servers, and basically the calculations are made using the R statistical package itself, making calls to a Bayesian engine called JAG. So all this is open source software. Uh, and of course, for anyone who would be interested, the actual calculation scripts, of course, we are happy to transfer them to anyone interested. And one thing that might be useful to note is that we are entirely blind to the data that is entered on the app website. So we collect absolutely no metadata. The only thing that we know, as I told you before, is that I know for how long the servers had the applications active every month. So I know, for example, every month that tool one was active for 350 hours. That's the only information I get. So if you have worries about confidentiality, yeah, there's no issue there. Okay, I'm sorry, I'm looking at the chat. If there's, I don't think this may be an issue. The attendance form, so nothing to do with me. So I'll continue. So the main features of the apps on our website and the calculation tool, they are web-based, but as I said, you can download a standalone version. One small issue that I noticed this morning is that the standalone version is not the latest. So it's still functional, but you might see small differences. Things that to put someone on mute. Apologies for that. So yeah, the calculations will be entirely fine, but you might see some functionalities might be a bit different between the offline and online version. Because one characteristic of Expostats is it's it's not a private endeavor. So basically, my weekend time and my personal money is what makes the tool work. So there's a comprehensive list of calculations, as everything that I presented yesterday and the day before is calculated on our tools. All the calculations are made using Bayesian statistics. And we try to create a relatively simple user interface and some infographics that facilitate risk communication. And it's free because it's basically powered by the University of Montreal, paying my salary. And there's, I think, interesting developments that will happen, I would say, within the next 3 years. We are going to start working on having a specific tools for noise. So you can already analyze noise exposure levels with Expostats, but you need to express your noise levels in either in dose, so in percentage, or in Pascal squared scale, because the actual pressure levels are like normal, but when you express them in decibels, they become normal. So I know several hygienists that use Expostat to interpret their noise exposure levels. So the typical approach would be, for example, to express their noise level in percent of the acceptable level, which would be, 8 hour at 85 dBA, typically. So you express your noise levels in percentage, and then you estimate the arithmetic mean, and you compare that to 100. So that would be the way to make a risk assessment. So you might say, okay, why not use the 95th percentile? As we discussed yesterday and the day before. Well, it's in the case of noise, it's very particular. It's a risk factor for which the dose response curves are so well done, so well known that they are the object of an ISO norm. And so there's an ISO norm that tells you exactly if you're exposed at this level for X number of years, you will get that kind of hearing loss. And in that norm, it is very clearly stated what is the risk metric for noise. And it's the long-term and the so-called energetic average that you need to compare to the acceptable level. And so if you want to do that using Expostats, you compare your noise, the arithmetic mean of your noise doses in percent to 100%. So, but we will create something more specific to noise in the near future. And finally, as I said yesterday, one big plus of Bayesian statistics is that you can incorporate external information in addition to your measurement data. So we will add that functionality fairly soon. Yeah, Aristides, it's exactly that. So if you express, let's say you have an exposure group, you have collected 6, why not 6 measurements? They're shift long measurements. And if you express them in percent, you can then put them in Expostats, and you look at the arithmetic mean instead of the exceedance fraction or the 95th percentile. And you would like to demonstrate that this arithmetic mean, so you can use upper confidence limit and so on and so forth, is below 100%. Or if you know, as Samantha suggested yesterday, if you want to have an action limit lower than the actual 100% threshold, you might use 50% or 70%, 75%. It's your judgment. And I wanted also to mention, take some time to mention a project associated with Expostats. So Expostats is the oldest set of tools, and it's the set of tools that is the best known that we produced. It's available on the web, and it uses, as I said, these open source Bayesian engines. And we conducted a project from 2015 to 2019 that was actually funded by IRSST, which is a Quebec research institution that is a bit like the American NIOSH. And so we obtained this grant. So it cost approximately 300,000 Canadian dollars, much less US dollars. And we were funded basically to free ourselves from using these free engines, but that came with very strict licenses, so nobody can use them and try to sell them or stuff like that. So what we did is basically all the calculations that are done in Expostats, we programmed them into 3 different languages. So we used the R, the statistical package, JavaScript, which is used for websites, and C#, which is a language that can be used to make software. And we put these algorithms available online. So anyone, for example, who would like to have the Expostats calculations within their own data management system. For example, if you're a consultant or a large company and you would like to have the Expostats within your own company system, you could freely take our algorithms, and if you have a programmer in your company, as many people would have, I guess, you can have them incorporate these calculations into your own system. Or even if you wanted to create a tool that you would sell yourself, you could do that. You could take our algorithms and then create your own tool and market it and sell it And the only thing we would ask is that you say these algorithms came from University of Montreal. So our aim in doing that was to facilitate the use of these Bayesian calculations, which we think, improve data interpretation, state-of-the-art methods in the industrial hygiene community. And the first offshoot of these algorithms we program is that we were able to create a Bayesian version of the IHStat software. So I think many of you might know IHStat and use it quite often. Myself, I still remember I got my first version of IHStat in 1998. 25 years ago on a floppy disk. So it's a fairly old piece of software that was updated a little bit some years ago. So what we did, basically, we took the old IHStat software that uses traditional equations to calculate upper confidence limits, and we boosted it, so to speak, with our Bayesian engine. And you see, we try to keep a very simple user interface, but you can see that we have additional results here in the new interface. And basically, what we try to do is to use the Expostats engine and put it into the the car structure that was IHStat. So you have still the looks of IHStat. It's still an Excel-based program, but the calculations themselves are performed using the same Bayesian calculation engine as in Expostats. So it is also listed IHStat base in the list of AIHA risk assessment tools if you go to their webpage. So since we will be using Expostats this morning, I'll tell you a little bit about IHStat base. But as you can imagine, it will be somewhat similar because it's the same calculation tool. So about your sample, your 6 values, for example, IHStat base will tell you sample size to check that the software correctly understood what you entered. And quantile plot, I mentioned it briefly. It's basically you try to evaluate whether your points are relatively evenly spread alongside a line, and that suggests that the log normal model is reasonable for your data. And more interesting, IHStat base will tell you also about, we do some statistical extrapolation, from your couple of measurement data to the exposure situation of interest to you. So, it's basically the stuff that I've been mentioning Monday, Tuesday, and yesterday. So point estimates and upper credible limits for the geometric mean and geometric standard deviation, the intrinsic log normal parameters that define the shape of the exposure distribution. And then for risk decisions, you will get point estimates and also 70% and 95% upper credible limits for the 3 parameters that we mentioned yesterday. So I write here any percentile, because one thing that we did is that if you prefer something other than the 95th percentile, maybe in your company you think it should be the 99th to be more stringent, or the 90th percentile, you can select that, you can change that. So any percentile, the exceedance fraction of the OEL, and the arithmetic mean. So these are the 3 parameters of focus. And one thing that's entirely new is that you get the probability of each AIHA exposure control category, so that we mentioned yesterday. And there's also a graphic that was on the old version 2, where was the estimated shape of the exposure distribution. So it looks like that. So everything's on the same screen. You see, very simple. You put your data here, and you have your OEL here. That's the only input, and then you click on Start, and the calculation starts. So since there's some data generation involved, you remember the 25,000 values that I mentioned yesterday, it takes, depending on your computer, it can take anywhere between 5 and 20 seconds. And it depends also on the sample size. If you input, I think someone tried with 2,000 values, so it took an hour. But usually, if you put below 10 samples, it's going to be around between 10 and 15 seconds. And so you got your numerical results here. You see here, try to use the pointer so you see better what I show, the quantile plot. So you can see that the points are reasonably spread alongside a line. This is the shape of the exposure distribution, estimated exposure distribution, and this would be your exposure category chart. And here in this example, in category 2 would be the likeliest, and the risk of overexposure would be very low at 1.1%. And one thing of note, you see here, because it's a Bayesian engine, we can input non-detects. So you can see here, smaller than 50, smaller than 30. It causes absolutely no problem, and it's interpreted correctly by the Bayesian engine. So there's no simplification that you don't see. Really, the Bayesian engine is able to understand the notion that measurement was, all we know about that measurement is that it was below some value. And to make a little bit of a zoom, this is, you remember on Monday, so Aristides, you don't need to treat the sensor data as I just showed here. You just input it with the smaller than sign. So if your lab told you this was smaller than 2 ppm, you just enter smaller than 2. That's all. And if you are lucky and the lab said, well, we detected the substance, but it could not quantify it, and so its value would be above the LOD but below the LOQ, then you can even do better than that. You can input a range. And for example, say we know it was higher than 0.2, but it was lower than 2. And so you can even enter in IHStat base a range using brackets. It's all in the small manual that we put online. So really, you don't have to transform anything, you just input the information that you have for each point. And here in this example, that is the first exercise that I asked you about on Monday, you know, this data set that I asked you to evaluate just by eyeballing the values with, you know, most of them were below half or very close to half the exposure limit. So you actually here have, it's a good example of why all my data below the OEL is not sufficient to feel safe. So these 6 points are below the OEL and are almost below half the OEL. And you see that when we create the AIHA exposure control categories, the risk of overexposure, so the chances that the 95th percentile is above the OEL are 70%. So it's quite an unacceptable situation, right? Despite most values were below half the OEL, it's very likely if we were able to measure a lot of points, it's very likely that many more than 5% of them would be about the OEL. So much more than for example, NIOSH advised would be reasonable. And to answer Samantha's question, there's no limit. You can, as I said, there's somebody already tried with 2,000 measurements. So your column will look a little weird because it's going to go much lower than the actual, result screen size. So you can really put any number of measurements. Both is the same for IHStat base and Expostats. Basically, the limitation is your computer limitation, because in Bayesian statistics, the computation time is going to be proportional to sample size. So for most of what is of interest to us in hygiene, so below 10, I would say, unfortunately, it will be very fast. In Expostats, instantaneous almost. In IHStat base, maybe 15 seconds. But if you input 5,000 points, it might take up to an hour. So the old limit from IHStat is not there anymore. And just to give you a brief, Samantha, tell me if that answered your question. And so a brief comparison between Expostats that we are going to use very soon together and IHStat base. So it's the same team behind the two tools. It's the same Bayesian engine. IHStat base uses the algorithms that we programmed during the C# algorithms that we programmed during the WebExpo project. The same philosophy in data interpretation. So what I said basically yesterday and Tuesday, sorry, and they are both free. So basically, the money that it comes from, so there was this funding for WebExpo, but basically every AIHA helped a little bit for IHStat base. We received, I think, $5,000, and I found myself from other research funds around $10,000 to create IHStat base. We are going to update IHStat base this year to be able for you to input an informed prior in the form of the AIHA category probabilities and add more languages, including Indonesian, I think. And so for that, AIHA kindly also offered $5,000 we will receive this spring. And myself also had to find basically siphoning money from other research projects. I think it's going to cost me 15,000 Canadian dollar to have the 2024 update of IHStat base. So that's why maybe sometimes you can see the user interface is not perfect, because all this is almost voluntary work. And the differences between the two tools, so Expostat is more web-based, and it has a little bit more results and customization than IHStat base, but you would see they are very similar. And unfortunately, that's a disadvantage of the new IHStat base compared to the old IHStat, is that there's a Bayesian add-in to the Excel file. And so if your company has a very stringent security setting for informatics, for computer related stuff, and And because it's Microsoft, there's a percentage of people for whom, unfortunately, iStatBase will never work. So that's something we cannot avoid. It's because it's Microsoft is always complicated. So that's a disadvantage of iHStatBase, that there's a chance that it might not work on your computer. But I must say that out of 100 questions about issues for iHStatBase that I received, maybe 2 were related to that problem, and 98 were people not reading the manual carefully. So read the manual carefully. So these are people that helped a lot, collaborators of these tools projects, scientists from a bit everywhere, scientists and programmers from a bit everywhere in the world. There's Peter Knott, a very friendly, very nice hygienist from Australia, people from France and from Canada. And so we're coming to the practical part. So I would invite you to go to our actual website, so which I'll copy paste in the chat. Find it. There we go. I'm gonna go there myself, and we can start together. Oops, sorry. Just to show you some slides still. Okay, so so you should have that on your slides yourself. So what we are gonna do, we're gonna go through the Tool 1 Express, which is a simpler version of Tool 1, to interpret the example from the first polling question. And so this is the actual sample. So if you don't have the slides with you, maybe you can write down these numbers. I'm going to switch between the two. I'll share the website. Okay. All right, so you should now see our web page, and as you see, the one I arrived at when I went to the website is the one in French. So I just click here on the little British flag, and I get the English interface. And there we navigate to interpretation tools. And this is where our 3 main tools are available. And if you click on one of them, you see it extends the box to an explanation in more details of what the tools do. So we're gonna use tool 1, and so you see there's in total 4 links. So there's 2 links for tool 1. So we have 2 servers running. So if one doesn't work very well, the other might do better. And the links below are the what we call Tool 1 Express, the simplified version of Tool 1, for which the customization is much less, and the results are simpler, but also it makes the tool simpler to understand. So we'll start with this one. And I hope it's going to work well for you, because I guess it has to do with the location of the servers. But when I did a course in Melbourne, in Australia in December, people had some trouble with the apps having, phasing out because of lag. So I hope it works well for you. You see, as you see, for me here in Canada, it works perfectly well. And I hope the servers communicate well with Indonesia and Africa. I remember giving some courses in South Africa where it went quite well, but last December in Australia was so-so. So this is the page that you see if you navigate to Tool 1 Express. So you should all be able to access this page. And I am going to enter the data here. So one thing that you can keep in mind is that it's very straightforward to do data entry in Expostat by copy pasting from Excel. So here I am typing manually the information about the concentrations. But usually it's quicker if you have your data already in Excel to copy paste, and it works very well. And also one thing you might notice is that every time I enter a new value, the calculations are automatically run. So that's a current characteristic of our tools, is that there's no run button or calculate button. Every time you change one of the inputs, the calculations are run. And since they are very fast, it doesn't matter much. So I verify my numbers: 25, 14, 52, 37, 2, and miss 1, 51. So that's our original data set. The exposure limit was 100, so I don't have to change it. And so you can see here on the left of the tool that we have exactly 4 different screens in that tool. So we limited the information we provide. One for descriptive statistics. So it is the one you see now. So this screen is only to check that your measured data seem reasonable. So you didn't make a mistake in data entry. You didn't input a measurement from another group by mistake with a very different exposure profile. So you can see here there's a number of very descriptive parameters. So you can verify that the software correctly read that you entered 6 values. And this is important because one thing that is difficult to manage is, depending on where you are in the world and the settings of your computer, Expostats might not like commas or dots for decimal points. And it's unpredictable. So sometimes in some parts of the world and in some computers, Expostats wants you to use comma. So for example, it would be 25.1. And you see that for my computer, Expostats doesn't like the commas. And for some other parts of the world and or other computers, it prefers decimal points. And you see here that indeed on my computer in Canada, Expostat likes decimal points as dots. So you can see some descriptive statistics here. And, some of them are actual risk metric, but these are calculated very simply without the Bayesian engine. So you should never use these to make your decision about the exposure distribution. This is entirely to check that your values are, you are right to input those values in Expostats. So this is on the top right, the quantile plot. So you can see that the data looks fairly reasonable. Not perfect, but there's no, ridiculously gross deviation. And if people like to present data as a box plot, here's a box plot of the values themselves, where you can see the box plot and the actual points themselves. Once you're satisfied that your data that you entered has been read properly and that is reasonable to put them into Expostats, you can go into the extrapolation part of Expostats. And these are the three remaining screens. So in the second screen, parameter estimates, Expostats will estimate for you point estimates and confidence intervals for all the parameters we mentioned in this course. So we have the geometric mean here, that would be estimated at 20, with a 90% confidence interval between 8 and 48. There would be the geometric standard deviation. So you can see the uncertainty is fairly high, 3.3, so a fairly variable situation. You can see the difficulty of estimating variability. The true GSD might be between 2.2 and 7.3, and 3.3 being the one corresponding to our own little sample. The exceedance fraction is estimated to be 9%. And it may be a fairly large uncertainty, 44. And you can also see the very large uncertainty. So you see a factor, an order of magnitude, as I mentioned Tuesday, between the lower and the upper limit, and the arithmetic mean, and also quite uncertain. So these are the point estimate, the point estimate and confidence intervals for the log normal exposure distribution parameters. There's also this plot where we imagine what you could see if you were able to measure 250 times for that situation. So it would look like that. And now if you want to go to the risk assessment, so people who prefer to do their decision-making with the confidence intervals, they can use this part here. So one note is that these are all 90% confidence intervals, which mean that all the upper limits, they are 95% confidence upper limits. Then we can go to the risk assessment section, where we have, the results that I mentioned yesterday, where we explain our framework, our probabilistic framework, and you can see here a summary of the situation. So the criterion defining overexposure in this tool is the 90th percentile above the OEL, and based on our models and the data, the probability of overexposure is 70%. And so you can see here that it's in the red zone, as we discussed yesterday. So that would be, in Expostats, we use the vocabulary polycontrol situation. You see on the right of the screen, you can see explanations for this vocabulary. So very simple and direct result. And finally, we added that not long, maybe last year, I think, following a request by AIHA, we added the exposure control category probabilities. And so you can see here, of course, we keep the same number here. Probability that the 95th percentile is above the OEL remains, of course, at 70%, but we have split the uncertainty distribution in using the AIHA categories. So we know the rest of the uncertainty distribution of the 95th percentile, 26% corresponds to the category 3 and 3% to category 2. And so this is what the simplified tool 1 provides you when you enter data. So just before we take a little break, I would like to continue with the what's on the slide, to just showcase when you showcase, sorry, I was reading the chat, to showcase the non-detect capability of Expostats. So, and on my slide, and I hope you can see yours too, we are going to replace the value 2 with smaller than 5. Maybe your lab is not optimal, the lab you have access to is not optimal, or you didn't measure for long enough. And so maybe instead of knowing that the actual exposure level was 2, the only thing you know is that it was smaller than 5. And you can see that it is very straightforward in Expostats. As you can see on the left here, I replaced by smaller than 5. So you can see it's very straightforward. You don't have to make calculation. You just use the smaller than sign and use the information provided to you by the lab. Of course, you need to, if the lab gave you a limit of quantification in concentration in the sample, you need to convert it back to a concentration in ppms in the air, or milligrams or micrograms per cubic meter. But otherwise, it's very simple. And there's even one further capability of Expostat, is that, and this is the example on the remaining part of the slide. So if you, for example, a perfect example for that, let's say you divided your day of exposure in 2 parts, and that in the morning it was non-detected or not quantified, but in the afternoon it was quantified. So the lab gives you a smaller than something for the morning and the value for the afternoon. Well, when you combine these 2 information, and on the slide that you have, it says smaller than 7 ppm for the morning and 20 ppm for the afternoon. When you combine these results, it's actually a range for the entire day. you know, because basically smaller than 7 is at minimum 0, right? And at maximum 7. So you can calculate a minimum value for the day and a maximum value for the day. And if you do the calculation, as you see on your slide, it would be between 10 and 13.5. So if you have smaller than 7 ppm for half the day and 20 ppm for the other half, what you know about exposure that day is between 10 and 13.5. So let's go into the descriptive statistics. No, sorry, the parameter estimates, where we have that for now smaller than 5 value. So we are going to replace the 14 value by the range. So as you can see, or do yourself, you simply use that kind of syntax in Expostats. You provide the range, and you see it doesn't cause any error. The Bayesian model can understand when you say something is between this and that. And so as you can see here, I said, you know, this was between 10 and 13.5. And to my knowledge, Expostat is the only tool that can understand that type of information. And I must underscore that if you have that type of information, or maybe you had the full day measurements, but the lab told you it was detected but not quantified, so you have actually a lower value and a higher value, you should use them, because saying that something was between 10 and 13 is a lot more information than if I just was able to say smaller than 13. So I don't really have time to explain a lot around that, but really, because basically when you say something was smaller than 13, it's a very large number of possible values, because, you know, we are in the log scale. So the Bayesian model is going to explore a lot of potential values between 13.5 and 0. And in the log scale, it's going to go towards very small negative number. Whereas if you enter a range, the number of potential values are much, much smaller. So if you want to reduce the uncertainty in your final estimate, you should do your utmost to provide a range instead of just smaller than, right? And maybe it's useful less often, but you also might well say to Expostats, this value is greater than something, right? So, so we can accommodate any type of censoring, which is the vocabulary, when we don't know the exact value beneath a measurement. We know that it was smaller than something, between this and that, or higher than something. This can be interpreted by the Bayesian model. Okay, I think we should take a break. So maybe a 5-minute break. So from 9, well, you know, for me it's 9:10 and up to 9:15. If it sounds reasonable, I'll see. But
Yeah.
I'm staying here. I still have coffee, so if people have questions, I'm remaining available.
Okay. Question, Prof. Jerome. If I have 5 samples and I only have one data detected that data and 4 undetected, can I still proceed the calculation using the tool?
Yeah, you can. It's as I said, the Bayesian model is able to understand that. The thing that you will remark is that your uncertainty is very high.
Yeah.
So if you look at the confidence intervals, for example, for the GSD, for the geometric mean, you will see they are very, very high. And so your limit of detection would need to be quite far from the OEL if you want to be able to make a decision.
Okay.
Otherwise, because of the very large uncertainty, you might not be able to reach 70% confidence or 95% confidence just because the non-detects are going to increase the uncertainty. So there's one situation that is really problematic where people should be careful is, and it's one discussion in our forums, the discourse forum, is that if you have almost only non-detects, and the limit of quantification is very close to the OEL, then it's difficult. It's a difficult situation, and you would need to be very careful. Because in that situation, I won't go into details, but we might chat at another point. But the prior in the Bayesian model is going to have a big influence on the conclusion. Okay. And so maybe further or deeper analysis is required. But it's only when the LOQ is close to the OEL. If you respect the recommendation that the LOQ should be 10% of the OEL, it should be fine.
Yeah. Okay. Thank you, Prof.
And to add, to profit from your question, Elsie, that's also a reason why if you can make your lab provide the information whether a non-quantified result was actually detected but not quantified or really not detected. This is very important, but because it can improve your analysis.
Yeah. Because from my experience, for some substances, our lab has limited capability in terms of detected the measurement result. For example, for benzene, currently several labs in Indonesia, the detection limit is below 0.03.
Okay.
And as you know, the current TLV, TWA from the ACGIS for the benzene is 0.2, 0.02 ppm.
Okay, so it's lower than the limit of detection.
Yeah.
Okay,
but
well, in that case, you can't. It doesn't work.
Yeah. That's why I think in this case, this one of the example where we cannot use the statistical tool, right? We need to exercise other, approach, for example, professional judgment, something like that.
Yeah, no, it's difficult. Well, I'll make a conference in Columbus at the AIHA conference, and maybe, hopefully later this year, I will be able to make a publication about that. But I have studied how high can be the LOQ compared to the OEL, and still we allow to make a good decision using, for example, EN 689. And what my preliminary results show is that if you use the bigger sample sizes, such as 9, instead of 6, your LOQ can be as close to the OEL as 80% of the OEL. So if your OEL is like 100 ppm and your LOQ is 80, so it's very close, but you have more samples, it doesn't, you can still make a reliable conclusion when you use the EN 689 recommendation, for example. So it's rather reassuring that it's not always mandatory entirely that you need to have the LOQ at 10% of the OEL. You can go closer, but then you have to take more samples. It's the basic conclusion. But maybe wait for the publication.
Okay, we're
For
looking
now, it's
forward.
just a hint.
Okay.
Okay, so maybe it's time I can give up to well 3 more minutes, maybe. Time to get coffee or something.
Question, Prof.
Yeah.
So let's say if you have the lab result below the LOD, right? But they
Yeah.
can still provide a number, let's say it's because the LOD, let's say 0.2 ppm, but they can provide a number, let's say they just mentioned less than 0.2 ppm. So do we have to before we key into the applications, do we have to divide it the result by 2 or by square root of 2?
Not at all. Not because when we used to do that, it was because with the old methods like IHStat, the old IHStat or the traditional frequentist method, they don't understand what smaller than 5, let's say, mean. The mathematics, they accept smaller than 5. So what we needed to do is to transform that reality into something that was understandable by the equations. So that's why we would say, well, we divide 5 smaller than 5, we transform it into 2.5 or 2 point something else if we divide by the square root of 2. So we needed to replace the intrinsic information that was smaller than 5 with an invented number, okay? But we don't need to do that anymore. The Bayesian framework understands what smaller than 5 means. So you really just need to input the actual information provided by the lab. The only thing you need to be careful, as I said, is that if the lab told you it's smaller than 2 micrograms in the sample, of course you need to transform that back into a concentration in the air. Does that make sense?
Okay, so we just key in the number of the LOD provided by the lab, right? If it is less than LOD number. So you just
if the lab tells you it was less than 2 ppm, you would enter what I put in the chat in Expostat. You would enter that in Expostat.
okay, just put less than 2, right? Okay, thank you, Prof.
Okay, so let's continue. Right. So if you go to section 2, maybe I'll just do a quick tour of tool 1 to show you some of the options that you have in tool 1 that are in addition to what we just looked at together, and then we can go in a couple of exercises. that you can do yourself. So I'll just go back and share my screen. Website. So if you go to tool 1, you will see that information. So the first thing that you might see is that the input part of the tool is much larger than it was in the simplified version. So you still have the exposure limit, but you have something new that we think might disappear at some point, but it's because it's not so useful. But as you can read the little box that pops up, the exposure limit multiplier was basically, we wanted to allow people to say, okay, I made my analysis with an OEL of 50 ppm. I would like to know how my results change if I used a lower OEL, let's say half my first attempt. So instead of typing 50 instead of 100 here, you would just say 0.5 in the multiplier. So you could keep your original exposure limit, but then say I want the analysis being done with twice the OEL or half the OEL. But it's not very difficult to actually change the OEL value, so that input might disappear. So more importantly, here you can, in the tool we discovered together, you can not select the level of confidence of the confidence intervals. It's set at 90 and you can't change it. Here in tool 1, you can. So it's here, credible interval probability. If you want 90% credible intervals, you can, the default is 90, but you can change it to whatever level you prefer. Also, one thing that is different from the simplify tool, you might remember in the simplify tool, well, it's just here. We have this 3-color scheme, which is the scheme I presented yesterday for, in the AIHA video, where we say, and the risk is between 0 and 5, it's the best situation. When it's between 5 and 30, it's still okay, it's tolerable. You remember the vocabulary. And when it's over 30, it's poorly controlled or unacceptable, or the situation where we need to act. Well, in tool 1, we allow you to actually customize your decision. So in tool 1, you don't actually have 3 colors, you only have 2, and you decide what is the separation between I will do something and I don't need to do anything. So by default, you can see that the risk of overexposure is the threshold is 30. So if I go to the, for example, to the 90th percentile tab, you should see soon. So you see here the difference. We don't have 3 colors. We only have green and red, and the division is using the value you entered here. And so since I use the default 30%, you can see that's this value, 30%, that separates green from red. So depending on it's your own judgment, the scheme I described yesterday is a proposal by 5 people. So it's not published in the AIHA book. It's 5 people, including me, that created that series of video, and we proposed this 5-30 scheme with green, orange, red. But if you want to use other threshold, for example, one natural threshold would be 50, and So that would be here. So the scale is not linear. That's why 50% you don't see half green, half red. But then, you know, when your risk of overexposure is above 30, it means that it's more likely to be a problem than it is not to be a problem. So you could decide above or below 50 is your threshold for action. So you see, it's allows you real customization of your risk decisions. So another difference from the simplified tool is each risk metric that we discussed has its own separate tab. So we have a tab for exceedance fraction, a tab for the 95th percentile, and a tab for the arithmetic mean, right? And of course, we have a descriptive tab too. And so two things that you might note is that you can, for example, if we go to exceedance, you can customize. You know, we said yesterday, NIOSH and everybody agreed that you know, not more than 5% of exposure levels should be above the OEL. Maybe you prefer to be something else. Maybe you are, for some chemicals that are maybe less worrisome, like I always use the acetone, which might be, you know, a flammable risk, but for health, maybe you wouldn't considering a very dangerous chemical. You might say, I would allow that 20% of exposure levels would be above the OEL instead of 5. And so you can change that. And the corollary of that customization of the exceedance fraction is that you can change the percentile of interest. So for an acceptable exceedance of 5% is going to be equivalent to looking at the 95th percentile. But if I prefer an acceptable exceedance fraction of 20%, I would choose then the 80th percentile, right? And so you can customize the percentile of interest. And when you change that, of course, the messages that you receive are changed. So let's say I change the 95th to the 80th percentile. So you can see if you look at the text below, if you are looking at my screen or doing the same yourself, that the risk decision criteria, what defines overexposure has changed to is the 90th percentile above the OEL. And then we say the probability that it is true is 32%. And since I set my threshold for action at 50, 32 is smaller than 50%, so we say it's adequately controlled. One last thing I wanted to show in tool 1 is that we have some graphics that we try to facilitate maybe the presentation of results to people less familiar with these concepts. So for exceedance, so there's ways to select the format, but what we try to do is to create these graphs where basically, so there's 4 variations of this graph and you can customize the colors, but basically we said, okay, an acceptable situation according to our choices, and you might say by NIOSH, if you use the same, is that out of 100 measurements we would make, if we were able to, 5 might be over the OEL. That would be what NIOSH tells us is acceptable. And then on the side, we say this is what we estimate from the data we input. So you see, it creates a way to show whether, you know, our data suggest there's a problem or not. So there's a variation of that, where on that graph on the right, we saw, the full red little symbols correspond to the point estimate, and the dashed symbols correspond to the upper limit. So you see, in that case, NIOSH will recommend that. We estimate like a 5 out of 100. We estimate there might be 14 out of 100, but given we only measured a couple of times, the truth might. So you see, it's an effort at communicating the notion of exceedance and uncertainty around it. And there's another where we put everything in a single graph, and another one again with a single graph with uncertainty, and the one in dark gray is what would be acceptable, and the rest what we think. So you see, we have made attempts at communicating risk. All right, so I want to switch to the exercises. So what I suggest we do is that I'll share in a moment the slide with the section 2 exercise. You probably can see it yourself, and I'll give you some time to try to do it, and then we look at the solution together. Sorry, there are some exams going on at the same time. I need to just see if there's no crisis going on. All right, so share the screen 2. Okay, so you should now see the section 2 exercise. So you will all use the same sample. It's a sample of the lead dataset that I presented yesterday and Tuesday. And we will use Tool 1 Express. Well, you will use Tool 1 Express, and we'll try to make a decision using 95% upper confidence limit. So not using risk of overexposure this time, but using the upper confidence limit. So you will use an OEL of 75 micrograms per cubic meter, so not the true TLV. So our overexposure criterion is 95th percentile above the OEL. That this is not met. And of course, if you remember, yes, switching between the various notions, this is equivalent to having the 95% upper confidence limit lower than the OEL. So the 4 steps that you need to take is first use so of course, enter your data. First, check the descriptive tabs so to vary log normal. Then find out point estimates for the geometric mean and geometric standard deviation. And then check the parameter, again, the same tab to find the point estimate for the 95th percentile, and more importantly, the 95% upper confidence limit, which is this value that we want to compare with the OEL. And finally, based on that, what would be your conclusion given our objective in the green box? So it should not be too long. So I propose I give you 5 minutes to go through that exercise using the simplified version of Tool 1. So you get to see whether Expostat works well in Indonesia or Tanzania, Zambia, and a second chance for Australia. It's 35 to the hour for me, so we'll look at the solution together at 40. So, Hanif, is that okay? Can you see the data now? I think now I share the actual exercise instructions. Okay, so it is time. I'll stop sharing the instructions to go to the actual tool. So here is what you see when you remain inactive for a while on the Expostat app. It's also what you might see if there's too many people at the same time, which should happen very rarely, or if the server's somehow tired. So you see it's grayish, and then there's a small message saying disconnected from the server. So you can refresh the page or just click on reload, and it's gonna start the tool again. So what I first do is input the right occupational exposure limit, and then enter the data. So 16.3. Okay, so first instruction, check the descriptive tab. So we are in the descriptive tab. The screen indeed tells us we have entered 6 points. Okay, none of them was non-detected. And we see some basic statistics, and none of them was above the OEL. On the right here of the screen, I can see that the data is reasonably log normal. There's no gross or extreme value. And you can see the actual box plot below. So one practical thing may be that is a bit of a drawback of our tools and a consequence of that is not a professional, payware, is that if you want to export the results or the graphs from Expostat, it's actually you need to use screenshots. And now in the modern Windows, the screenshot tool, you can actually select the part of the screen that you want. So that makes it fairly easy to share your Expostats results, but we have no export functionality. That's a limitation of Expostats. But you should, manage fairly well using the screenshot ability. So now we go to the parameter estimate tab. That's where we're gonna be able to answer the second question. The point estimate for the geometric mean and geometric standard deviation. So the geometric mean, we have it here. So for that exposure distribution, we estimate the geometric mean to be 17 micrograms per cubic meter, sorry. And the geometric standard deviation would be 1.7. So a fairly low variability for these measurements, which we can, see. We can guess just looking at the data, not very variable, with a factor 3 between the minimum and the maximum, and it is reflected in the value 1.7 here. Then if we check again the same tab to get point estimate of the 95th percentile, well, I think it's fairly easy to find. So the point estimate for the 95th percentile is 41.8. And the credible interval is between 27 and 101. And so this is where, remember on Tuesday, I described the trick when you have an interval to get the upper and lower limit to have the proper level of confidence. So you need to remember that all credible or confidence intervals in this tool are 90% credible intervals, which means that the upper limit is a 95% upper confidence limit. So the value we seek, if you look at your instruction, it's the 95% upper confidence limit on the 95th percentile. This value would be this one, right? So 101 would be the 95% upper confidence limit for that situation. And so what would be the conclusion if someone wants to try in the chat? What would be the conclusion for this situation? Volunteer risking typing his belief in the chat. Okay, right. So no volunteers. So I'll kill the suspense, and of course, we would conclude that this situation is poorly controlled or unacceptable or whatever vocabulary or requiring action, whatever vocabulary you would like to use, since the upper confidence limit, the 95% upper confidence limit is above the OEL, we would conclude that we did not reach 95% confidence that the situation was acceptable. So we would say it's poorly controlled according to the instructions that this exercise provided, right? And maybe we can go have a look, since I see the time advancing, we can have a look together at, if we look at the same situation, but using, leaving aside the confidence limit and the confidence intervals, but using the risk of overexposure notion. So I go to then risk assessment. And of course, as I mentioned, the decisions will be the same. These are just different ways of interpreting the same uncertainty, right? So here, what we see is that, the criterion defining overexposure, of course, is the one, the usual one, 95th percentile above the OEL. And here, so we can see here in the text or in the on the speed meter here, the chances that this is true is 10.9%. So the risk of a problem is 10%. So it is higher than 5%, which is the same as saying we could not reach 95% certainty that there would be no problem. So it confirms, of course, it confirms our decision. So if, according to my instructions, we wanted to demonstrate that to have 95% certainty that there would be no problem, we now can calculate that the probability of a problem is exactly 10%. So we did not meet our objective here. But you see here, it's a clearer, in my opinion, a clearer message. according to this data set, the chances that this situation corresponds to overexposure is 10%. And if we interpret this value using the three colors that we discussed yesterday, we would be in a tolerable situation. And if we use the European guideline, which says that the risk should be lower than 30, well, we would say this is acceptable, right? Because we managed to reach at least 70% certainty that there is no problem. Or if I continue circling around, we are sure that the chances that there is a problem are below 30%, and because we estimate them at 10. Okay, so I see time passing, so I don't think we will have the time to go much further in the exercises. Maybe I should leave time for some questions. It's 8 minutes before the end. You are of course free to continue do the following exercises on your own, and if you have any question, I'd be happy to answer them later. You can ask them on the forum or by email. And maybe one last thing to show, you remember this notion of screening steps where we said if we have one value that is very low or a number of values that are very low, we maybe don't need to go collect 5 or 6 samples. So what I just do here is show you the statistical foundation for these screening steps, which can be reproduced in Expostats. So let's say I have an exposure limit of 100, and you remember the screening steps. The one in EN69 says, for example, 3 measurements below 1/10 of DOEL. So I'm going to put 3 values here that are not the same to create some variability, but all below 1/10 of DOEL. And we can see what are the risk of overexposure according to Expostats. So let's say I put one fairly close to 1/10, let's say 9. One fairly lower than that to generate some variability, let's say 4, and one that would be somewhat in, let's say 8, right? So if I just go to the parameter estimates, you see that I generated a reasonable variability, a GSD of 2. And if I go to the risk assessment tab, you see that I am in the green zone. So the risk of overexposure is indeed fairly low. So you can reproduce, so to speak, the statistical foundation underpinning the use of the screening steps, where if you have a few values very low, then you might be okay. And reversely, if I have one value above DOEL, we can also have a look. Let's say I have one value just above DOEL, 105, and you can see here that the likelihood that the situation is problematic is fairly high. So you can see again, the rationale for these screening steps one way or another. So I'll stop there, I think. And again, I'm much thankful for you attending this course despite the unusual hours. And if there's anything, any question, please, you can go ahead now or later if you want to contact me.
Okay, thank you, Professor Jerome. So is there any question for Jerome before we close the session? We still have few minutes. No, I think we are all, processing the information.
Yeah.
Okay, Jerome. In the early, I forgot to introduce myself. So, hello everyone. I'm Elsia Asafira. I'm the former president of the Indonesian Industrial Hygiene Association, and currently I'm with the board of advisor of the association. So on behalf of the association, I would like to, again, we are very grateful for having Jerome providing the session for us. And I have to extend my gratitude also to the Australian Institute of Occupational Hygienists, because I met Jerome during the AIOH conference in Melbourne last December. And I was very surprised. Jerome is very kind, yeah, and he's willing to provide this free online course for us in Indonesia, and also colleagues from Tanzania, Zambia, and also from Australia. So let's give a big applause to Jerome. Okay, everyone.
Thank you.
Okay, I would also present a certificate of appreciation symbolically. Oti, can you share screen of the certificate? Okay, I think the computer is getting tired, yeah.
Like
We haven't
everyone.
seen, yeah. So
Okay.
because
Oh,
it's
that's nice.
far away, yeah, Jerome, we would like to present the certificate of appreciation, and we wish that we could also have the opportunity for more collaboration with you in the future. And
Course,
for the,
yeah.
and for the participants, we will send you the certificate of attendance for each session that you have attended, and also a link of YouTube channel. I'm sure that we need to, listen again, yeah, the record, so we can fully understand about the statistical tools that Jerome has been teaching us for the last 3 days. I think that's it, Jerome. If you have, any closing remarks for all of us.
Well, no, not really. I think I find it very admirable that you would use this very difficult, time in your day where you have family and other, in addition to your work, to try to improve your industrial hygiene skills. So it's very admirable in my opinion. So I applaud your efforts, and I think it's my job at the university to try to convey some of the research and translate it so that it can be useful for practitioners. So I'm very happy when I can do that. And I'm very thankful that you thought that might be useful to your practice. And yeah, thank you again. And I hope maybe I'll meet some of you in the future somewhere on the earth.
Yeah, hopefully. Okay, again, thank you so much, Jerome. And let's close the session. And good night, everyone.
Yeah. Bye-bye, everyone. Have a
Bye-bye.
good
Thank you
night.
so much.